let's start with where we left basically. So next we will discuss variational pins, abbreviated as vPINNs. So those who have some background in finite element method.
You are muted.
Yeah. So those who are having background in finite element method, they are aware of the variational principles and method of weighted residual. So basically, vPINN was first proposed by Kharazmi from our group. So idea is the same. So as typical weighted residual form. So although they use the term variational, this is not a variational formulation. So this is a weighted a method of weighted residual. So you have a PD, which is given by this term LU xt, and you just multiply with the test function and then integrate over time. So basically, this is the PD, and this is the right-hand side. F of x is the forcing term. So you are multiplying both with the test function and integrating it over the full computational domain omega. Okay, and this actually gives you this bilinear form given by this expression here. Okay, and depending on the choice of the test function and the trial function, you end up with the different schemes. So we will discuss that. So basically now this is your residue. So basically this is called as a variational residue. Okay, so instead of a strong form, now you are using a weak form of the PD. Okay. So this okay, let's. Okay, so different choices of test function V and the trial solution U theta will result in different formulation. So if you choose Dirac delta function as a test function and the trial function as collocation, and you end up with the PINN, original PINN. Okay, if your test function are global polynomials with the Galerkin trial function, you end up with vPINN. That's what we are discussing now. And then there are other methods that has been already proposed in the literature, like if you use piecewise polynomial as a test function and again Galerkin as a trial function, you end up with this var net, variational net. And the same author proposed HP vPINN. So instead of single domain, you split the domain. So you can do both H and P refinement, basically. Okay. And so on. So here, the last one, they used basically the least square trial function, and they end up with DGM. So if your test function is unity, you end up with the finite volume method. Okay, so here we are going to discuss HP vPINN, vPINN and HP vPINN both. Okay, so as I said, the same author, they propose HP vPINN by domain decomposition, and they use Petro-Galerkin subdomain methods where they can actually do both H and P refinement. Okay, so let's take an example. Let's start with simple one-dimensional Poisson equation. Okay, and you have the particular boundary condition, and basically it's a we know the exact solution. It's basically a fabricated solution. And then what we are doing, we are actually finding the variational loss function by multiplying the, you first divide the computational domain into an elements, number of elements, non-overlapping elements, and then you just multiply the test function in each element, and yeah, you just sum it over all the elements. So this is your residual loss term, variational residual term. So there are various ways to perform this integration. So for example, I'm showing, yeah.
How can that, it depends on what G is, right? You put that red over there.
Yes. So, no. What I'm saying, I'm assuming the solution of the form, this. And then I'm finding G accordingly.
So the problem is find, is a problem to find G.
No. This is still a forward problem, but I'm assuming I know the exact solution. So for comparison. So what I am saying that here I'm finding G based on the exact solution. Okay, and now I'm trying to solve that that problem, and finally I'll compare my prediction from the neural pins with the exact solution. So this is basically a fabricated solution. So any question? Okay. So there are various ways to perform that integral. So either you don't shift the derivative, keep it as it is. That's the first expression. Second, you shift one derivative. Okay. So you end up with the boundary term here. Okay. Or third, you shift both the derivative. Okay. So basically, in this formulation, we use second expression here, where we are shifting the derivative. So advantage here is when you are calculating this derivative using automatic differentiation, you are reducing the computational cost because you are reducing the order of the derivative here. Okay. And rest of the things are pretty much the same. Here, the only novelty is your loss function is loss function is variational loss function instead of the strong form of the loss. Okay. So basically you end up with this expression, the variational loss. So you have the integral term here plus the boundary terms which are coming in the second expression. And now you define the number of test function. This is basically a model formulation, not the nodal. So you need to define number of modes which you are using. In this work, the author used legendary polynomial as the test function. So for each element defined the variational residual, you have to transform that back to the parent domain using the affine mapping, so that you can compute the integral in the parent domain and map it back to the physical domain. Okay. Sorry? This one. You just I'm skipping the steps, but yes. So that's why I said I'm skipping some step, but if you perform the algebra, you end up with this expression for all the three integrals. This one. Maybe I need to I need to go back and see why that half is coming. So, sorry? No, that's not the.
No, but I guess that because we have two values, right? It's like an average.
We have two values at the end. Yes.
Yeah, so this is like an L2 thing, right?
I need to go back and see. What?
You take the gradient by the base, and generally this is the MSC thing. This is for the boundary that we are having. So that's the MSC thing. So we generally add 1/2 to the MSC so that the gradient is consistent.
Okay. So so what we are doing here, we use different cases. So if you see the first column, this gives the exact versus vPINN comparison, and the second column is the absolute pointwise error. So in the first column, we just use single element. So you can see the boundaries of the element from -1 to 1. So it is given by the blue dash lines. In the second row, that's for first row. Second row, we use 2 elements. So you can see the boundary here. And the third, we use 3 elements. One here, second, and third. And then we actually did, we just changed the number of test function and the number of quadrature points. So because all these integrals are strongly depends on the quadrature which you are using to approximate the integrals. And of course, the number of test function, the modal functions which you are using. So you can see that with increase in number of elements, you are getting better and better results. So this is really surprising because the variational vPINN formulation gives you much better results than original PIN. It's because of reduced you are actually shifting the derivative, so you are reducing the order of the derivative here. So that could be the one reason, because you don't have to evaluate higher order derivatives using AD. So as you increase the order of the derivatives, your accuracy actually reduces, even using automatic differentiation. It all depends. Yes. Yes.
These are global tests.
Global test function. Yeah. So for element 1, but then if you increase the number of element, then it become a local test function. In each element, you are using 20 test function. So this is basically niche refinement, what we are doing here. Okay, in the next plot, again, it's the same thing. Single element, first row, 2 elements, second row, and 3 elements, third row. But now here you can see the number of test function is 60. Previously it was 20. So you can observe that the solution actually improves compared to the last one. But still, it's not good. But if you increase the number of elements, the solution become much more accurate. And you can see the pointwise error here. You never get -6, -7 using PIN. So vPINN is more accurate than PIN. And the third case, we actually use, we have just changed the quadrature points. So from 80, we just reduce it to 20, and then you can see the, so basically the variational PIN, when you use this, there are so many factors you need to consider. How many test function you are using, what is the quadrature rule, how many points you are using, and of course, if you can refine the computational domain with number of elements, both H and P. You can do P refinement with increasing the number of test function, and H refinement with the number of elements. So you can improve the solution pretty much. So let's move on to the next idea, which is the multi-fidelity PIN, or in short, MPINN. So it was proposed by Sukhoi Meng and the Karniadakis. So idea here is to map the low fidelity data into the high fidelity one, and then feed it to the PIN. So how you are mapping, you are just learning the correlation between low and high fidelity data. And then once you learn the correlation, you just map the low fidelity data into high fidelity before sending it to PIN. Okay, so the author proposed composite neural network. So here is the idea. So basically, this is the correlation between high and low fidelity data. So YL is the low fidelity data, and YH is the high fidelity data. Here, rho of X are and delta are the multiplicative and the additive correlation surrogate constant. If you see that this is what people have used in even co-ringing method and other methods where they have multi-fidelity data set. But this relation does not actually account for the nonlinearity in the relation code. So what they have done is they actually defined these two functions. So this is actually the they're splitting this function correlation function into an linear part and the nonlinear part. Okay. So they are not defining what kind of function is, but they are just defining, they are trying to learn that function through the neural network. Okay. And here is the idea. So you have the first neural network, which actually it's fed with the low fidelity data. Okay. And then you actually get the, you get the solution, which is low fidelity one. Okay. So basically, this is the data value at these locations. Okay. And now you also have high fidelity locations where you have high fidelity data, which you are supplying as the input along with YL to the linear part of the network and non-linear part of the network to learn the correlation. And finally, you will get the high fidelity data. Okay. Now, you will use that high fidelity data for the PIN computation, right? Is there any question? Basically, instead of defining the correlation like this, you are defining the correlation into two parts. One is linear, one is non-linear. Okay. Sorry. Instead of these two. No, basically, when you say you have a non-linear part, you can actually use non-linear activation function. So if it is just a linear part, then you don't need that. You have a very simple network. Okay, so that's the reason you can actually. So I'll give an example here. A data with low fidelity means it's kind of data which has noise, lot of more noise. High fidelity is more accurate than low fidelity data. So you're mapping the noisy data on a high the accurate data set, and then you are feeding that into the PIN network. Let's take an example. ReLU is not linear; it is non-linear.
So what do you mean?
You don't need to give an activation, right? It's identity.
Can I ask a question?
Yes.
How do we already know the linear and the nonlinear part? Is it or is it is to be estimated?
No, we are estimating that part using neural networks.
So then when you are saying that correlation, I mean, if I'm thinking of like some normalized data, then correlation already is a bilinear form. So I don't understand what is a nonlinear part over there.
So sorry, you said bilinear form?
Yeah, the correlation when you are looking at the normalized data, then it's already some sort of a it's a bilinear form on the data. Okay. So I don't understand what is the nonlinear part in that.
So basically, this is very simple correlation, right? It's difficult to include the nonlinearity here unless you have, these are based basically the multiplicative constant. It could be nonlinear, okay. But what these guys they have done, they just split the linear and nonlinear part separately instead of learning this rho and delta.
Okay.
So they just propose a combination of linear and nonlinear correlation. And the aim is to learn these Fi and Fnl, the linear and nonlinear part, using two different neural networks.
So linear would be some sort of a first order approximation and nonlinear will be the rest?
Yes, yes.
I see. Thank you.
So yeah, let's take an example. So we have a low fidelity data set, which is given by this expression. And we have high fidelity data set. again given by this expression. So now we have XL, which are the locations of low fidelity data from 0 to 1 in steps of 0.1. And we have just 4, so these are total 11 numbers. So we have at 11 location, we have low fidelity data, and at these 4 locations, we have high fidelity data. Okay. So you can see that these blue dots are the high fidelity data, and these red dots, I think it should be 0.01. Sorry, it's my mistake. It's not 0.1, it's 0.01. So we have a lot of low fidelity data sets. So the red dots, okay. So, and this is the correlation that we are actually predicting using the neural network. So this is your YL and this is your YH, okay. So when we actually trains the multi-fidelity neural network, they are learning both linear and non-linear part. And then you can actually see that they are exactly predicting the mapping, okay. So once you have that mapping, you just map the low fidelity data set onto high fidelity, right? And then use it for PINNs. So the whole point here is to learn this nonlinear mapping, okay, the correlation map. Yeah, it's a pre-processing before sending that data into a PINN. Of course, PINN can handle noisy data. As I said, there are many frameworks like Bayesian framework, where you can actually feed the noisy data set, and then instead of point estimate, you get the confidence interval. Okay. But this is another way. If you have combination of data with low and high fidelity, then you can actually use multi-fidelity PINNs. So I think we have already discussed these things. So I'll quickly go to the example. But if you have any questions, you can ask me before proceeding. Sorry? So, when you are solving for inverse problem, then you don't have any alternative, right? So you cannot compare there, right? But for forward problem, of course, I said that for forward problem, PINN is not yet competitive with the traditional numerical method.
That's fine.
Yes, it's very expensive. What do you mean by that? I mean, it all depends on how much data you have or what's the model, how big your model is. So eventually the question is, can you fit the model into a single GPU or you need a multiple GPU, right? Can you saturate the data? I mean, if you cannot saturate, for example, if you have data that has been, it just saturate one GPU, then of course you need multiple GPU. So it all depends on the model and the data which you have. Yeah. I mean, you mean to say instead of variational kind of thing? I mean, eventually you need to somehow incorporate the physics, either in a strong form or weak form, right? Or the variational form. The third approach is variational form. But yeah, these are the only ways you can incorporate physics. So, okay, let's move on to the coding part. Just stop here. So you can download the code from that. Yeah, I'm opening just. Okay. Okay. So this is the first example. This is again a Burgess equation. We have already seen this example a couple of times before. So okay, I'll just go step by step. So these are the things what we are importing. So basically, this is a TF1 code, which I am actually running in TF2. So that's why I'm disabling all the TF2 behavior here. Okay, so you can easily run TF1 code. Okay, and these are the standard things which actually you need to import, like NumPy library, matplotlib for plotting, SciPy for uploading the data, which I have saved in the .mat file, and then other things like PIDL that actually imports Latin hypercube sampling function, which you can use to sample the points. Okay, and then there are things like grid data to plot for plotting and the time for measuring the computational cost. So you start with this. I don't know how many of you are doing, but if you have any doubt, just please let me know. You start with this main file. So you first define the diffusion coefficient. And you don't have any noise in the data, so it's 0. So this is basically number of data points which are actually coming from the initial or boundary condition. Now you are defining the residual points, number of residual points. Okay, and here you have to define what's the input layer. So we have input X and T. So 2 is the input, and then these are the hidden layers. So I have 6 hidden layers, each containing 20 neurons. Okay, and my output is just single. It's just one. It's U, right? Which you are calculating on all XT points. Okay, defined by this enough 8,000 points. So here I'm. So this is the layer feed-forward neural network architecture. And here I'm just uploading the data. Okay, so this file is available on that folder, Burgess._shock. So this is basically an exact solution. So I have in time direction. So I have 256 cross 100 size for basically U. See. Okay. So once you upload the data, you just take all the variables. So I also store T, X separately. Okay, and this is the exact solution. And now I'm creating, since I have stored T and X in a vector, so I'm just using mesh grid to create a grid. Okay. Okay, and then X star is my is a vector where I'm actually horizontally stacking both X and T values on the top of each other. Okay, and U star is my exact value. I'm flattening it out. Okay, these bounds I need to define for normalization. So this will actually give you the minimum and maximum from X star. And okay, here is the important thing where you are actually finding creating a data set. So this is boundary plus initial data. So what I'm doing, I'm actually taking the last rows of this X and T. So I'm just taking this line, this and these 3 lines. So this actually constitutes the your data. Those are actually a part of your initial and boundary condition. Okay, once you get the data, so that's the training data you need to vertically stack. So I'm stacking vertically from the exact solution, but you can also feed it separately. So if you don't have exact solution, but you know the initial and boundary condition, you can supply it. So eventually we need all these vectors. Okay. So what I'm doing, I'm just adding the location of these data points.
Can I, please?
Yes.
Yes. The initial condition you set it.
Sorry. So the initial condition is the sine wave, negative of sine wave, which we discussed earlier. Is the same viscous Berger problem which we discussed earlier. We actually use the what is called as spectral methods to get the reference solution. This is not exact, but the reference solution. Okay, and we actually extracting the initial and boundary points from the data, exact data.
So all the point on the initial points are taken into account.
So these are all the points on the initial values and the boundary points. But eventually then we will select the points, we will sample it from this set basically. So we are not going to take all the points.
Okay.
Yeah, so we will see that. Yeah. Okay, now you have to create the, so now you got the locations for the training data, that means initial and boundary. Then you have to create the residual points. So you can see that you have the lower bound and the upper bound, and I'm using the Latin hypercube sampling. Okay, so it actually just creates the random points in that computational domain. Okay, and how many points are we need? NF. NF is your residual points. So I am creating 8,000 random points in the domain. Next, you vertically stack both data points, data plus residual points. Okay, and okay, this is the training data which you already have. So you have locations for boundary and initial, and the value of the solution at those locations. Okay. Okay, now here is the sampling part. Now you need to. So you need to sample random points from the training data as well as, well, here there is just one training data. So I'm asking, I'm using the random normal distribution. Okay, and I'm taking NU points. That means 100 points, data points, randomly from the initial and the boundary locations. Okay, which you have already stored in XU, right? These are the locations of data points. Okay, and once you have now the location of data points and its solution, now this is where you will actually feed this part to the neural network of PINNs. Now next step is create the model. Okay, so you need to supply location of data points, value of that data points at that location. You also need to supply residual points, the architecture, what is the layer. So you have already defined the architecture here. Okay. Lower bound, upper bound, and also you need to supply this viscosity coefficient. Yes, yes. Okay, let's go to the PINN class. So here are the values which you have supplied already. And now I'm just using the self so basically when you use self dot that particular value, you can actually call it from anywhere. You don't have to call it within the particular class or subroutine. So I'm just splitting the x and t value here. So you have xu, which is the data set. Okay. So the first part is x and second part is t. Similarly, xf is the residual points. The first part is the x locations and the second part is t locations. So they are xt points basically, right? And then layers nu. And here you are initializing the neural network. So you are supplying the layers. What's the number of layer? What is the architecture? And you will get the weights and biases. So that's the initialization. Let's see how it works. So you create the null vectors for weights and biases, and the number of layers you already know. That's the input here. And then actually use Xavier initialization to initialize the weights and biases. Okay. And here you are just appending the things. So, okay. And you are returning weights and biases. Okay. So now this is the session where you are actually, you are creating a session here with this syntax. And now you are defining a placeholder. So placeholder basically, again, it's a variable whose value can be defined at later stage, because a priori you do not know. Yeah, you are creating a session. It's a TensorFlow session to run the TensorFlow code. Yeah. So now you are feeding all the values. So xu, tu, these are the location of x and t data points and the solution at those locations. And then these are the residual points location x and t. And okay, now this is important. So now the first part is the data mismatch term. Basically, this is the term which you are getting from the neural network data. So what you are doing, you are supplying the location of x and u for data points. That's the input to the neural network, and output of the neural network is u, right? So that's the u predicted from the neural network. Okay, and this is your PD residual. Okay. So here you are supplying the location of residual points x and t, and it gives you f predict. So let's see this one by one. So net u. Okay. Okay. Here is the net u. You are supplying x and t. You are just concatenating those things along with the weights and bias. So these are self dots, so you can call it from anywhere. You have already got this from initialization neural network. And you are supplying that to the neural network. Okay, so this is the neural network. You just you don't need this basically. Okay, so you have weights, biases, and the x vector, which is the concatenation of x and t. And then you create the feed-forward neural network. So from 0 to number of layers -2, because in layers you have input and output layer, you just remove it. And then you get all the hidden layers, right? And then just use tan h activation function. You multiply h and with w. So h is your input first. And then you add bias. Okay. And then you apply activation function. And this will actually happen over all the hidden layers. This is a for loop. Okay. And at the end, you have weights and biases. You can see that again, I'm doing the same thing, input multiply by weights plus biases. And now here there is no activation. So it's a linear layer. The last layer is the linear layer. Okay. So this way you will get the neural network output. And this neural network output is your U, which is actually you are calling from netu.
Excuse me.
Yes.
In that particular function that you are talking about right now, yeah, to in a neural network function. Yes.
Okay, this one.
Yes. So here you are finding the time hyperbolic. So we need h, which is the input basically.
Yes. Sorry. So even if you remove this, you can still feed x directly. So I just need to change here h to x, but you can keep this. This is just a normalization, okay, within lower and upper bound.
Yeah.
Okay, so let's move to the PD residual. So you are supplying location x and t. So here are x and t. When you supply it to net u, you will get solution at those locations, residual points. And now you take gradient of u with respect to t, gradient of u with respect to x, and gradient of ux, which you get here with respect to x to get the double derivative. Okay, and this is again automatic differentiation part. You don't have to do anything. And once you get this value, you just find the residue ut plus ux minus nu times uxx. Yes. Yeah. Well, for TF1, you don't have option to choose directly forward or reverse, but in JAX you have option to choose which mode you want. You can do it in TF2 also, but it's not that simple. So JAX gives you the more flexibility. You can choose which mode, automatic differentiation mode you want. Yes. It's in TensorFlow. Yeah, it's a TF library. Okay, so what we are returning is the PD residue here. Okay, so now you get the data points, data value predicted by the neural network and the PD residue here. Now just create the loss function. So loss function consists of, okay, the first part is the PD residue. You are just taking the minimum, the mean of that. Okay. And second term is the data mismatch term. Okay, here is the neural network output, and here this is the value. It's a placeholder. Basically, you will feed later during the training stage. Okay, so we will feed that. So now we are initializing the optimizer. I'm using Adam optimizer here, and this is the learning rate. Okay, and I'm minimizing the loss function using Adam optimizer here. Okay, so these are the syntax you need for global variable initializers. Okay, and now we are running this session. So let's see, since we created model, now the next step is to train the model. Okay, so this is the number of steps which we have given here, and let's look at the train part. Okay, so this is what we are supplying, a number of iteration, 1000. I'm just adding the MSc history here, and here this is the TF dictionary. So now what are the placeholder which you have defined earlier? Now you can feed the data in those placeholder from the TF dictionary. So these are the placeholder which we have already created. So we have 1, 2, 3, 4, 5 placeholder here. And for all the placeholders, we will actually create the, we will feed the actual values. So these are the actual values. It is the same. So XU TF gets XU, which is the location of data points, X location of data points, which you have already defined here. Okay. Similarly, TU TF will give you the location of T location of data points, and same for the residual points. Okay. Now start the session, and now you can actually find the loss function value at each iteration, and you can print that value here. Okay, and then you just add all these loss function, append it in the MSc history so that you can later plot it. Okay, and you're returning the MSc history here. So this is what we will get after training. And the next step, once you train it, next step is the prediction. Once you train it, you have trained the model. Now, next step is you can actually feed different set of residual points, not the same which you have used, or you can use the same thing, because there is no issue of generalization here. It's not like classification problem where you are trained on one set of data and testing it on unseen data set. Yes, so here your network is trained. The only thing what you are changing is the residual point location, but you will always get more or less same accuracy, no matter, as long as your residual points are actually coming from the same computational domain. If you are changing the domain, then it will not work. Okay, so prediction. So what you are supplying, you are actually supplying the X star value. We have already stored the X and T value in X star. You can see that the mesh grid value we have already stored, horizontally stacking, and you are supplying that value. And now you are actually calling the session, and you are calling uPredict and fPredict, so that this will give you the solution at the at the given residual point, predicted solution. And this is the PD residue, fPredict, basically. Okay, and you can see that you are, okay, when you call this, you need XU and TU values. And this is actually, you are calling this function. Yeah, netu, this function. So this way you can actually predict the solution on these residual points. And once you get, the rest is just you are finding error since you have the exact solution. This is the L2 norm, U star, which is the exact solution, which we already have here. And uPredict is the predicted solution by the neural network. Okay, you print the error, and then for plotting, you just use grid data. And you can also plot the error. So these are the figures where we are plotting the history, the loss function history, exact solution, PIN prediction, and the pointwise error. So let's run this. See, I'm running it for just 1,000 iterations, but okay, something is wrong. Oh, okay, sorry. So I have saved this in data file. PD residue. So no, you have to show that PD residue is very small, right, at each location. A residue of PD at every collocation point. Yeah, residual points. So this will give you loss at every iteration. You can see that the loss is -2. Okay. Okay, so this is the loss function, how it goes down with number of iteration. This is the exact value. Okay. This is the predicted value, which is not good after 1,000 iteration. You need to run it for more number of iteration. And then you can also show the pointwise error. Okay. So if you are already running, just try to run for say 10,000 iteration or something like that. so that you can see the your losses going down, and you can get much better accuracy. So we will modify this code for the subsequent part where we will discuss the performance improvement technique. So is there any question? If you are not clear about the code, you can even email me later on. So I'm not hoping that you will get everything in that code in one shot, but you can email me.
So TensorFlow has an evaluation function. But why did you implement your own
Prediction? This is the old code which I'm showing. But yes, TensorFlow has evaluation functions.
When I see some of the examples, they require a tape.
Yeah, I mean there is no tape here because this is TF1. So the tape concept is there in TF2. Okay, so you need to create a tape for differentiation, and then once you differentiate, you get the derivatives. You just kill that tape. If you have second derivative, you need to create two tapes. So here in TF1, there is no tape concept here. Okay, so I'll just move to the lecture 2.
There are some questions in the chat.
Yes. Is there any numerical convergence rate of the solution when it becomes larger and larger? First of all, yes, if NF, if you are increasing NF, the convergence, I would not say convergence, but the accuracy increases. The other implication is that when you increase NF, you are making it more computationally expensive because you have to find out these derivatives on large number of points compared to when your NF is small. But well, there is no concept of numerical convergence because we do not know what is the numerical scheme that automatic differentiation uses behind the door. Okay, I mean, what exact weights they are using to calculate the derivative using chain rule of differentiation. But yes, you can show that it converges when you increases NF, but at the same time, it becomes expensive.
Sorry, you have the exact solution and you have a computed solution. So
yes,
you can have an estimation of that error with respect to the number of points.
Yes.
And is it possible to have something that is order 1 or the 1/2? I don't know.
No, what well, you can show, but it is not a universal. I mean, it all depends on problem at hand. So you cannot say that when you double the NF, your error will be half or something like that. Okay. It all depends on what kind of problem you are solving.
Okay, thanks.
And I have a question.
Yes.
So in the code, there is an array called layers, and it has 6 layers with 20. The
Yes.
number of each layer is 20. So those 20 are number of neurons.
20 are number of neurons and 6 are the number of hidden layers. So you have 6 hidden layers with 20 neurons in each layer.
Is there at least some guideline to how to set those numbers?
As I said, these are the hyperparameters. You need to predefine this before solving. Of course, a priori, you do not know how many neurons you need or what kind of how deep your network should be. But the general guidelines is if you have a complex solution, then you need a network, deep network, say above 6 or 8 hidden layers. So in this case, since we are solving Burgess equation, we have the discontinuous, not discontinuous, but high gradient region. You can see that you cannot capture that region if you just use 3 hidden layers, and you can, no matter how long you run, but you cannot capture that high gradient. So you can play with the number of neurons and number of hidden layers and try to run it for large number of iteration and see the results. So you can, but as I said earlier, also there are different technique like dropout, or these are used when you do not know a priori how what should be the network architecture. You start with a very big network, and then you drop off the number of neurons, or even the layer itself, or the weights, the connections, if they are not contributing. So this is the concept of dropout.
And I would assume the similar thing for learning rate, setting the learning rate.
Yes, but then there are papers where people, they propose the adaptive learning rate. So basically, what you are doing, you are there are various versions of that. So there is something called a cyclic learning rate, where you are cyclically increasing and decreasing the value of learning rate, so that if you're stuck in the local minima, you can get rid of you get out of the get out of that. Okay. Then there is something called as learning rate annealing. So basically, what you do, you start with a very large learning rate initially, and then suddenly you decrease the learning rate after some iteration, because then you can actually make sure that you do not stuck in the local minimum because of the initial large value of learning rate.
Okay, thank you.
Okay. So let's start with the.
I have another question. Sorry. My question is about here the example.
Yeah, I'll come to that. Yeah.
Sorry.
Sorry.
Yes, I have another question, please.
I didn't get your question. Can you repeat it?
Yes, I didn't get it. Now is the question. You showed the example with boundary condition that was fixed. But if we have a hyperbolic problem, for example, we know that boundary condition can be given on one boundary and not on the other. Should this work also in the same way?
Yes,
or
yes,
some difficulty
yes.
there?
Well, if you have already seen our first example, we have randomly chosen boundary data points, so they are not continuous. So in lecture 1, so you can actually
they are taken everywhere on the boundary. Can we just select on the incoming boundary, for example?
Yes, you can select, but the accuracy will strongly depends on what where you are selecting the data points. Because as I said earlier, as you are going away from the data points, your solution accuracy degrades. Because eventually you are fitting the, it's not evolution algorithm. So it's a regression algorithm where you are fitting the solution in XT domain.
Okay, thank you. So there is some difficulty in that what you are saying.
Yes, yes. But yeah, there are techniques which we'll discuss how to overcome some of the limitations of PINN.
Okay.
Yeah, so let's quickly go. So quick recap, we have already seen these things, the basics of deep learning and the physics informed deep learning. In the second lecture, we will see some of the limitations of PINNs and performance improvement techniques. How can we overcome these limitations? So, okay, I need to, or if you are already running the code, you can actually make the viscosity coefficient 0, okay? And again, try to, run the code, and then you will see that it is not converging, okay? So I can show you, just need to stop here and okay. Okay, so here is the viscosity coefficient. And I'll just run this again. I'll keep this loss function as it is so that we can compare the value. Sorry? Yes, it's an inviscid Burgess. So you don't have viscosity term.
But then what's the reason for it to not converge?
As I said, when they are calculating this automatic differentiation, they are taking information from all directions. So it's like a central difference kind of thing. So which will not work when you are calculating that nonlinear term, which has where the information is coming in particular direction. So you need kind of upwinding basically to get it right, the nonlinear part. So okay, so let's try to run this. So I just made viscosity nu equal to 0. No. Yeah, eventually you are actually using some kind of numerical scheme, right? So the chain rule of differentiation is also some kind of numerical scheme. I need to kill the kernel. Hold on. So you may not see the difference because I'm just running it for 1000 iteration. Maybe I need to run it for longer iteration. Yes. You cannot. Oh, there is not much difference. So maybe I need to run it for longer time. Yes, I mean, the whole point is eventually you will not get the solution here because of your automatic differentiation is not correct for the nonlinear term. Okay, so that's the point. So what's the remedy? It's the same what you have actually doing it for hyperbolic conservation law. You just add the small amount of numerical diffusion. That's what you do, right? Here, you can actually add the same thing, but in the strong form. So you come up with the, what people have done, they have just added the a new part instead of just solving this inviscid Burgess equation. They have added a new part, but with small NU, 10 to the power -3, -4. And in some cases, they have also learned that NU just to make these solution, stable. But at the same time, it doesn't. It should not explode. No, the point here is a priori you do not know what kind of numerical coefficient you need to use, right? Just for -3, -4. So in one case they have actually learned that coefficient. Yeah, that's a parameter. Okay. So So there are many, there are many things where PIN can fail, basically. So we will discuss this. So one of them, I have already shown that. Okay, so what are the limitations? So first one is the chaotic nature of the solution. So if you have chaotic nature, then it's really challenging to capture. So for example, we have solved the Kurmatov-Siwasinski equation, which is the fourth order PD. And with proper initial condition, it can become chaotic after some time. So we have seen difficulty in training pins for forward problem basically. So it couldn't even solve the problem. Next is if you have stiffness in the solution. If you have, say for example, slow moving manifolds, and at the same time you also have fast moving manifolds, like stiff chemical kinetics, where some of the species are evolving faster than the other, then again pin faces difficulties. So then in that case, you need to use, well, vanilla pin faces difficulty, but then there are some architecture where they separate the pin. One is for slowly moving manifolds, and another is for fast moving manifolds. But yes, stiffness is a problem. Then the presence of higher order derivative. As I said, even though you are using automatic differentiation, but the error increases if you have very higher order of derivative. So that's another difficulty pin faces. Sampling collocation points. So a priori, you do not know where to take collocation or residual points. So we are using, we are actually selecting the random points. So when you have discontinuities or kink in the solution, or even for turbulence problem where you have a laminar region and highly turbulent region, you need more points in that region. Okay. So we have used RAR, residual adaptive refinement. So we actually find out the points where your loss function is high, and in the neighborhood we introduces additional residual points. Okay, and so that it can actually reduce the loss function in that region. So that's the residual adaptive refinement. But if you don't do this, then there is no way you can improve the solution. Another issue is the soft constraint. So when you add a penalty term, you are not sure whether that term is satisfied or not. Okay, so this is called as soft constraint issue. Okay, so well, there are different methods in the literature. We will discuss some of them here. How to make sure all these soft constraints are satisfied in a hard sense. Okay. Again, this is related to the weighting of the different loss function. You need to enforce large weights on the data points or residual points so that it you actually enforce this constraint in a hard sense. Optimizer is again a bottleneck for PIN because it all depends on how efficient your optimizer is. And since you are solving highly non-convex, high dimensional optimization problem, that's basically the one of the issue in terms of accuracy. So the problem which we have solved, the best accuracy we get is of the order of -5 or maximum -6, but not more than that. So you cannot compare accuracy with the spectral methods or spectral element methods. Yeah, so another thing is capturing high frequency. If you have high frequency in the solution, then it's again a bottleneck. PIN has shown to a struggle for these frequencies. There is something called as F principle, frequency principle. This is what is called as spectral bias problem. Okay, so basically PIN first capture low frequency first, and then actually goes for high frequency. Okay. Fail to capture periodic solution. So when you enforce periodicity in the solution, I'll show you that. I think I have the one slide for that. So this is a serious problem for PIN. It actually satisfies the periodic solution, but I'll show you what's the issue. I have one slide. And as I said earlier, long time integration. So this is again an issue. As you go away from the initial condition, the error increases for long time integration. So then people have come up with domain decomposition strategies like the one which we discussed in time, so that you can actually overcome this kind of issues. Again, the gradient flow pathologies where you have unbalanced gradient. When you do the back propagation, you need gradient of the loss function. But then you have loss function consists of data mismatch term and the residual term. So when you take the gradient, you have to take gradient of data mismatch term and the residual term, and which can have different magnitude. Okay, so that is called as gradient flow pathologies. So when you back propagate it, that will create a problem. Okay. Okay, I'm not sure, but yeah, I'll check it and I'll get back. So let's see we'll discuss these performance improvement techniques. So first one is adaptive activation function, dynamic weights, NTK-based weights. So NTK is the neural tangent kernel based weights, and self-adaptive weights, and finally the unified time domain decomposition framework. So let's start with adaptive activation function. So as I said, there is no thumb rule for choosing activation functions, right? There are many open issues while training, like vanishing and exploding gradient, and even a plateau phenomena. If you have flat the region, then the gradient is 0. So this is the empirical observation. Basically, a well-chosen activation function can help gradient descent to not only converge fast, but to generalize as well. Okay, this is basically for classification problem. What are the desired features of activation functions? So nonlinearity, continuously differentiable, and the range. Okay. However, there is no thumb rule, as I said. So that is the basic motivation for adaptive activation function. So you start with a particular activation function and then adapt it as per the problem at hand. That's the idea. So what we are doing, so basically this calligraphic nk-1 z is that bilinear form wx plus b. Okay, and z is the input instead of x. So what we are doing, and phi is again the activation function. Okay, so instead of this term, we are replacing that with this term. So this is the additional term, n into a. Okay, so what is n? N is a positive scaling factor. Okay, and a is a tunable activation slope. Okay, and how you are initializing that? You are initializing na is equal to 1. So you are always starting with this term because na is 1. But now you are adapting a, fixing n, adapting a. So if I choose n is equal to 10, okay, I'll start with a is equal to 0.1, right? So now what I'm saying that my network, I'm just saying that, okay, I have this kind of activation, but now I have parameter whose value is 1. So it will change a value if the loss is decreasing. Okay, so it all depends on the optimizer. Just like weights and biases, it will actually adapt the a value. Okay, and for different a value, 0.5, 1, 2, and 3, you can see these activation function, how they are changing the slope. Okay, so sigmoid, tan h, ReLU, and leaky ReLU. This has been incorporated in NVIDIA's modular software, where they actually use PINN. Well, one thing is this is you are defining globally. Okay, that means there is just one parameter for the whole network, but then you can also define it locally. So this is for each layer k, and this is for each layer k as well as neuron I. Okay, so this is the neuron wise activation function, adaptive activation function, and this is the layer wise. Okay, so I'm not going into the details of the theorem, but yes, for the most basic gradient descent update, you can show that if you have at least one of the following 3 conditions, like constant learning rate, diminishing learning rate, or adaptive learning rate, then you can show that you will never get stuck into the suboptimal critical points. So that means basically what the adaptive activation is doing, it is dynamically changing the loss landscape. So if you are stuck in the local minima, it is actually changing the loss landscape so that you can come out of the local minima. Okay. Okay, here is the generalized framework for adaptive activation function. So instead of single activation function phi, I am actually using set of activation functions phi1, phi2 till phi k for every layer. Okay, for every hidden layer. Okay, so phi1 is my standard activation function. Take tan h or sigmoid or anything, and phi2 from k equal to 2 to capital K, I am using this sinusoidal activation function. So this is similar to the Fourier features. So you are incorporating Fourier features in the network. What's the advantage? You can play with the frequency of this sinusoidal function, and because they are actually multiplied with the scaling factor A. And you can also multiply the parameter A along with N. So basically it's like you have the standard activation function, and on the top of that activation function, you are adding a sinusoidal noise. Okay. So what's the point here? This can actually overcome the spectral bias problem. So now, due to these Fourier features, you can actually capture the high frequency in the solution. So how you are capturing, because your frequency itself is a parameter. So the network can increase the frequency of these phi2 to phi k activation function in order to capture the given complex solution. So I'll show you the example. Okay, let's start with the simple example. This is a function approximation. So you have data points, and you are trying to fit the function through that data points. Okay, so no PDE part. It's not PIN, it's just a function approximation. So you have function here from x minus 3 to 3, and we just use randomly chosen 300 data points from minus 3 to 3. We use tan h activation function, and the loss function is just a data mismatch term. There is no PDE residue. And you can see here the fixed activation function. So I'm not sure if it is visible. It's 22,000, 8,000, and 1,000 iteration. So you can see the red curve after 1,000 iteration, the blue line after 8,000 iteration, and the yellow cross after 22,000 iteration. So you can see that it fails to capture this sinusoidal part. Okay, but if you use the adaptive activation function global, this is global, so you can actually capture in 22,000. So you can see that how that area variable changes. So this is the loss function. The red curve is for fixed activation function, and the green is for adaptive activation function. You can see on the right hand side, this is NA. So basically, you are initializing NA as 1. That's what I said. And then you are adapting A, fixing N. So you can see that as the A changes, your loss function is decreasing faster, right? And after some time, it saturates, okay? Because there is no improvement here. You can see the saturation of loss. Okay, so adaptive activation function can give you better convergence. And if you see the red curve, it is stuck in the global minimum, local minimum. There is no improvement in the loss function. No, we change the parameter of the activation function, the A. So what we are doing, the optimizer itself is changing along with weights and biases. Yes, yes. No, I'm not showing this. This is a global. So I'll come to that one. The spectral bias, the Kronecker, deep Kronecker networks, right? So I'll come to that one. Okay. So basically, one thing I forgot. This is called Rowdy activation function. Rowdy means oscillatory. So I'll come to that. No. This is the global part. So we have just NA. That's it. So the first example, what I'm showing is for global adaptive activation function. So only A is the adaptive part, one single parameter. And we are initializing that NA is equal to 1. So that's what I have shown here. So if you see this, so we have initialized NA is equal to 1. And now the optimizer is adapting both weights, biases, and A, such that the loss should decrease. So it is actually changing the slope of the activation function. Yes, yes, yes. On the same my Github page. No, no, it's not available, but it's just one line code. I'll do it. So I'll show you. Okay, so what we are doing, we are actually defining weights and biases. That's the initializing we are neural network, right? So you just need to define additional parameter A. So I'm defining A is equal to 0.1. It's a variable. And in the loss function, since it's 0.1, N should be 10. So now this is your adaptive activation function. So basically what you are doing is, so along with weights and biases, you also get A value from the optimizer. And then just need to change this. No, we don't. I mean, the automatic differentiation will adapt automatically. So we don't have to explicitly, we just need to define that as a parameter along with weights and biases. So we don't have to explicitly find a gradient and all. And that's it. It's just one line change in the, so you just need to define A and just multiply here with N into A. Sorry. So this is, yes, because I am choosing N is equal to 10. So I said that NA should be equal to 1. Yeah. So 10 into 0.1 is 1, right? A changes. So initially it's 0.1, but now it is changed. N is fixed. Not activation function. Here we are changing the slope of the activation function. So the slope of tan H. Oh, okay. We don't have to explicitly show, instruct it to the network. We just need to make sure it's a part of the parameter. Here. Okay. So like this. Okay. Okay. Yeah, that's correct. Earlier. No, it's my mistake. It should be A. It should be A. Yeah, it's fixed. So it's just one. Yeah. Yes. I think that's it. Then actually you can print not just iteration and loss value, but you can also print A. You can also show the values and how A is changing. But okay, we don't need this. So now you can see how A is changing in every iteration. So it's easy to incorporate these adaptive activation functions. I'll stop here because I'm not plotting a.
So how do we choose the value of n? Because do we choose it arbitrarily? So because if the value of n is very high, then it will have stiffness, right? So for the activation function.
Yes. Yeah, it's a good question. So I'll explain that in a moment. So okay, so where is the duster? Yes. Can you see the board?
Can you move the camera slightly down? Then I can see the complete board.
Can you now see the board?
Yes.
Okay. Yes. So okay, the question is what he asked, how to choose them. Okay. So basically, this is the hyperparameters we have to define it a priori. So the point here is, so when you choose, so for example, NA is equal to 1, that's the initialization. And when you choose n is equal to 10, your A should be 0.1. So if you increase the n value, say n is equal to say 100, A should be 0.01, right? Okay. So you can see that my A value is decreasing, and when you update A value using gradient descent formula, you have to use the learning rate. So for example, an plus 1 should be equal to an minus learning rate NL and the gradient of the A, basically with respect to all the parameters, right? So for example, I have n value, n optimal star is equal to say 2, okay? And if I increase n equal to 100, I started A is equal to 0.01, and I'm actually going towards that A star using this update. So it all depends on your learning rate, right? So it will take a lot of time if you go from 0.01 to 2 rather from 0.1 to 2, right? So this is one catch. Second thing, if you increase n value, say very large, so that actually creates some kind of numerical instability, because this value should not be lesser than my learning rate. Okay, because learning rate is large, you are not learning anything. It's very small value, right? So you need to be very careful by choosing n. But for most of the problem, n is equal to 10 works. Okay, so this is the hyperparameter you have to define. I hope it clears your doubt.
Yes, kind of. So basically, hyperparameter choosing is sometimes based on trial and error basis. So
yes,
it depends on the optimal solution of your problem.
Yes, yes.
Yeah, thank you.
Anything else?
No, that's all. Thank you.
Okay, so let's move on to the another example. Now it's PINN here. So we are solving 2D Helmholtz equation. Again, you can see the Helmholtz equation, and we assume the exact solution in this form: sine phi pi x multiplied by sine 10 pi y. And we are finding G based on the exact solution. So finally, we are comparing the predicted solution with the exact solution. So now activation is Stanage, it's adaptive, 8,000 residual points, 200 data points, learning rate 8e-4, and we just use Adam optimizer. So here we use fixed activation function. This is the blue line. This is the locally layer-wise adaptive activation function, which actually performs better than global one, which I have shown earlier. And this one is the Rowdy activation function. So now these are the Fourier features which we are incorporating, those sinusoidal features. So you can see that the loss function and the relative L2 error. So if you have high frequencies, say for example, you start, I just use 5 pi x and 10 pi y, but if you say use 100 pi x and 100 pi y, then there is no way you can converge using fixed activation function, no matter what kind of activation you use. So you need a kind of, these Fourier feature Rowdy activation functions where you are incorporating noise along the base activation function Phi1. So you can see that the relative L2 error is decreasing much faster. Okay, one point here is, of course, they are expensive, the Rowdy activation functions, because you have multiple terms, not just single activation function, but K activation functions. So you can, for most of the problem, you can start with K is equal to 2. So that will somehow mitigate the computational cost. But then since as I said, the frequency is a learnable parameter, the Rowdy part will actually captures high frequency much faster than the locally adaptive or global activation or even fixed activation. No, you are adding that. Can you see you are adding this thing? And then you are feeding it to the next layer. Yes. No, we are adding directly. We are not averaging. Sorry?
The bias?
Yes, the bias will come. So we have bias here. And of course, the weights are there. So we are adding bias, and then we are taking. So basically, this is just an activation function. It's a sign activation, right? So it's just Wx plus B. That's the argument of that activation function. Yeah. But then you have the frequency, which is learnable. Yeah, I mean, that's what we need, Rowdy activation, because otherwise you cannot capture high frequency waves. So basically, for that, you need some intuition, right? So when you say that, okay, I have some kind of a shock region, it's high frequency, right? Then when you do say, for example, domain decomposition, then you can use Rowdy part only in that region. And or else recently we have come up with the adaptive domain decomposition. So a priori, we do not know how to decompose the domain. Okay, so we are learning that decompositions basically. Okay, so when you learn and then you decide how to initialize the PIN with deep network or shallow network and with activation, this Rowdy part or not.
This functions work very well for non-custom examples. Things like, let's say, here when we say high frequency, we generated periodic intention. Let's say,
so we use that for Euler equations. If you see the CPIN conservative PIN paper, the last example is for Euler equation, where we use adaptive activation function. In recent paper, JCP paper, we again use domain decomposition and the adaptive activation function, and it has been shown that it can capture the shock really well, almost exactly. I don't have results in the slides, but I can show you the paper. Okay, let's move on to the next technique. This is called dynamic weights. Okay, so I already said this. So the basic mode of failure for vanilla PIN is this imbalance back propagation of the gradients. So you have two different terms, data mismatch and the PD terms. Okay, so Wang and Paris group, they actually come up with this dynamic weight idea. So idea is very simple. So let's start with the gradient descent update formula. And you have gradient of J is equal to gradient of JR residue plus JD data. Okay. And you can use the Taylor expansion for which actually expand near theta n plus 1. Okay. And now you put 1 into 2 and you end up with this expression basically. Okay. So you have minus of eta. Eta is your learning rate. Gradient of loss function, that's the quadratic term, and then half of eta square and this term. Okay. You can write down as L2 norm here for this term, and you can actually split this term loss function into two parts, the residue parts and the data parts. And now you just multiply this inside. So you get first term, second term, and third term. And now let's focus on this three term. Okay. So we have these three terms here. So I'm just multiplying and divide with L2 norm here. Okay. Like this. And now I'm dividing this ratio as X. So I'm defining this ratio as X. And this term where I'm actually doing orthogonal orthonormal diagonalization. So you have Q transpose diagonal matrix into Q. Okay. And then X, so basically QX is Y. That's how we are defining. So you get Y transpose, diagonal term, and Y. And finally, you end up with this summation term here. Okay. And what are lambdas? Lambdas are the eigenvalues of these loss function. I'll come to that. So similarly, when you plug this expression here, so you will end up with this expressions. Okay. It's just one or two steps. Okay. From this expression, you can see that if you want to converge, then this should always be this should be small. I mean, theta n plus 1 loss value at n plus 1 layer should be lesser than loss value at nth level. Okay. And it strongly depends on the eigenvalues of eigenvalues lambda. So basically, this lambda I, lambda IR, and lambda ID are the eigenvalues of this gradient second order or Hessian of loss function, total loss function, the PD part, and the data part. Okay. Okay. So if the gradient flow is stiff, then some of the eigenvalues of this part may be large. So we may not get the condition what I said. So you get this minus this should greater than 0. Okay. And that's why PIN fails to converge to the correct solution. So what's the idea here? Idea is to learn, basically it's a learning rate annealing approach. So idea is to actually, use the moving average for this lambda. Okay. So you define this lambda, which are the eigenvalues of loss function, second derivative. So you calculate maximum of JR. JR is for the PD, and then divide with the J. So JI basically the ith. This is basically so okay. So before that, this is the PD part, and this is all the remaining penalty term. So I don't have M terms. I have just one term, which is data mismatch term. Okay. So what I'm doing is I'm taking maximum of JR, which is the PD loss term, and I'm dividing that with the absolute value of JD, in this case, JI. Okay. So that's my lambda I value. Okay. And then you actually use the moving average part. Okay. So instead of, so once you get lambda hat, this should be hat here. This is not lambda. Then you take the moving average and then come up with the lambda I term. So for alpha, they use 0.9. Okay. And they have defined it for all M terms, but we have just one term, one data mismatch term. And once you get that alpha, you just plug that into the updated formula. And actually that actually balances the gradient of both the terms. So we will see some examples how they are balancing. Okay, another idea, the same dynamic weight, instead of using learning rate annealing, so what they, in the same paper, what they have defined is the attention mechanism. So I already I just said transformer, so that is the attention-based mechanism. And the skip connection. So you can see that this is the network, the feed-forward neural network you have. And now you have another network on the top, which has same input but different output. And you have another network. So these are transformer networks. Okay, and the output of these two transformer networks are basically the skip connections for your feed-forward neural network. Okay, so you can see it is the same mathematics you have. You just need to. So W1 and W2 they are not square. So these are two different weights and biases. So basically, the idea of skip connection is you can actually improve the stability of the algorithm by actually adding the features of the input to some subsequent layer after the first layer. So that's the idea here. So I'm not going into the details of the transformer network, how they are performing, but the whole idea here is to use skip connections. Okay, so that's what they are using. So somehow some part of the input features they are actually transferring to the next layers. Okay, not just the first layer. Okay. Let's see the example. It's a two-dimensional Helmholtz equation. Again, our assumed solution is of the form like this. And you can find out right-hand side using the exact solution. You just split your loss function into PD part and the boundary term. And the aim is to estimate this lambda. Okay. So I'm using just two hidden layer with 30 neurons and the learning rate this much. And the activation function is hyperbolic tangent. Okay. So aim is to learn lambda. So what I'm doing, I'm using the learning rate annealing approach. So I am actually calculating lambda using this expression. Okay. At every at every iteration, and then I'm plotting that value. So initially, since I do not know the value of lambda, I start with 1. So this is the vanilla pin. Okay. And you can see that we started with 1. It actually increases the lambda value, but then it actually saturated almost near 5. Okay. So we will compare this approach with the vanilla pin. So if you see the relative L2 error, so we just ran the same experiment 10 times, and we are reporting the mean value of the relative L2 error. So the mean value for vanilla pin is 9.4 into 10 to the power minus 2. With learning it annealing, it goes to -3, 2.0 -3. And then with transformers, with skip connection, it is of the same order. And if you use both learning rate annealing along with the skip connection, it again gives the same order of accuracy, -3. So you can see that compared to vanilla pin, your solution improves almost by 1 order of magnitude. Okay, more than that, in fact. Okay.
How do you know that you have to apply this?
Sorry?
How do you know that you have to apply this?
The basic intuition is the gradients of the PD residue and the gradients of the boundary terms, they are not same. So I'll show you this pictorial. So, okay, here. So you can see that I have plotted the gradients of the, so you can see this is the blue line, which is the gradients of the data points. And this is the orange line, gradients of the PD residue, F. Okay. So I'm comparing this at every layer. So I have 2 hidden layer and this is the final layer. Okay. So you can see that The blue, which is the data gradient, is very high compared to the PDE. So when you back propagate it, you're not learning anything. Basically, you are missing one term. So the whole point is to balance those gradients. Okay. So here also you can see, so this is the vanilla pin, first row. In each layer, you have large data gradients, but small PD gradients. So when we use learning rate annealing, you can see that the magnitude of data gradient reduces substantially. This is the log scale, basically, the vertical axis. In all the three, transformer networks with skip connection, learning rate annealing, and the combination of these two, you can actually mitigate this gradient imbalance. So that's the whole idea of, the back propagation algorithm is not aware that which term is important. Okay, so it will give equal importance to all the penalty terms. But what we are saying that when we solve PDE, our first important term is the data, because unless and until you force network to satisfy boundary condition, next step is to satisfy PDE. Right? You cannot first satisfy PD and then look for boundary condition, right? So that's the catch here. So that's how we are actually learning that parameter lambda, which is the weight of the your data term. So this way you can actually overcome many limitations of PIN where actually PIN fails. And in fact, you can accelerate the training and even you can get better predictive accuracy. Yeah.
So in the transformer playing the role here, or is it just the better?
No, the skip connection. Skip connection is the, yes. So if you use just residual ResNet, then as I said, some of the input features are actually you're transforming it to the subsequent layer, which is important to learn the solution. So that's what. Yes.
So this is in effect considering different penalty terms for the data term and the PDE term.
Yes. You can, yes, we have also tried that, but see, for example, the adaptive activation function trick, if you use, you have to adapt the lambda as per this expression, right? As one of the parameters. No, but it all depends, again, it boils down to your learning rate, how fast you are learning. But when you use the ratio term, sorry, where it is. Yeah. So this ratio term, you know exactly how much magnitude you need for lambda, right? So if you see this term, so it suddenly increases, it goes to 40, but then it realizes, okay, we don't need that much. So it will slowly come down and then actually converge it to, this value. But in order to go to, from 0 to, so you can see that it goes to this value in just say 1000 iterations, but you may not get if you start with this one, right? If your lambda learning rate is -4, so if you want to go from 0 to 1, you need 10 to the power 4 iteration, right? Okay, let's move on to the next concept. It's the same thing as dynamic weights, but you are defining those dynamic weight using neural intelligent kernel. Again, the same author, they proposed this idea, NTK. Okay, so I'll just go to the mathematics. So this is your gradient update formula. Okay, so you rearrange this, you just rearrange and take limit n tends to infinity. So you get this ODE basically. Okay, now your loss term consists of this loss term, consists of just a data mismatch term, no PD. So you end up with this expression. Okay, and now you just multiply this transpose term both sides. So this is again a transpose term, and then you just cross out this d theta and you end up with dt u theta by dt, and with this term. Okay, so this equation 9 is the neural network dynamics in function space. So basically this term, the product term is your neural tangent kernel, and it actually does not change with respect to iteration. So T is actually the iteration. So it always stays constant. Okay. Moreover, it is important to note that NTK is positive definite for almost all over-parameterized neural network. I mean, most of the neural network which you use, they are over-parameterized because the number of data are always less than number of parameters in the network. Okay. For pins, it depends on, say, for example, forward problem, then yes, because forward problem does not have much data. But for inverse problem, basically, we make sure that our network is over-parameterized. Number of parameters are more. Otherwise, it is difficult to learn the pattern or the using that much of data. It's under-parameterized network basically. So you need to make sure that it should be over-parameterized. The over-parameterized network generalizes well compared to the under-parameterized. So as I said, this NTK kernel, it actually remains constant throughout the training period. Okay. So this actually basically enables us to examine the training dynamics of PINNs through the lens of limiting NTK. So what we are doing now, instead of data mismatch term, we also have the PDE term. So you have PDE term here. And now instead of a single scalar value, now you have matrix, NTK matrix. Okay. So this calligraphic KUU is for data term. This is for residue term, and these are the mixed term, UR and RU. Okay. So basically, this is positive definite matrix. These are the entries of these elements of NTK matrix, KUU. So you can see just U theta at the data point, Xi, whereas KUR this is for data points and this is for the residue points. Okay. So these are the entries. So basically, this is the dot product in a product. So again, as I said, the kernel K does not change during training. So what we are doing, we are replacing T with 0 because they are almost same here. And you can actually solve this using, say, variable separable method, right? And you can end up with this solution. Okay, this is exponential. You just take the, rearrange it and take log and take, integrate it, and then you end up with this exponential term here. Okay, so variable separable. Okay, now once you have that, you just subtract this vector from both sides. Okay, and this is basically the orthogonalization of K. So you just replaced this NTK with Q transpose capital lambda Q. Okay, and then you end up with this expression. Okay. Okay. So so if you see on left hand side, you have data mismatch term and the PDE term. So if you want to converge this term, it strongly depends on the eigenvalues of the NTK matrix. Okay. So that's what I discussed. So NTK kernel's eigenvalue describe how rapidly the optimization error decreases because of this expression. And jth component of RHS will approximate only decay by the exponential lambda JT rate, because you already have this term here. Okay. Okay. So the whole point is to define this lambda, basically capital lambda. Okay. So, okay, let's come up with some examples. So we have this PDE term. Now we have this lambda R that needs to be defined, and that's need to be learned basically, and lambda D for the data term. Okay. So what we are doing, we are actually directly altering the eigenvalues of NTK matrix by defining, by multiplying this term with the corresponding elements of the NTK vector matrix. Okay. And to overcome the discrepancy between these elements, KUU and KRR, we are defining lambda value like this. So this is the trace of NTK divided by trace of KUU. And lambda R is trace of K divided by trace of KRR. Okay. So the dominant eigenvalues of KUU are less than that of KRR. So we end up with lambda D greater than lambda R. Okay. So is it clear here? So we are still trying to balance these two terms, the data mismatch term and the PD term, through the eigenvalues of the NTK matrix. Okay. So let's see the example here. It's a 1D wave equation with the initial condition U and UT. And we already have the exact solution, which is obtained using D'Alembert formula. We use 3 hidden layers, 50 neuron, learning rate is this one, and time H activation. So now we have 3 terms here, lambda U, lambda UT. So these are for data mismatch term, initial initial condition, and the lambda R is for the PD. So our aim is to learn this lambda U, lambda UT, and lambda R, okay, which are initialized unity in the beginning. I'll show you the solution first. That's the first row is the vanilla PINN. So you have exact solution. This is the predicted solution. Everything is same, number of iteration, activation, all the hyperparameters are same, except one is just unity weights and one is with NTK weights. Okay. So you can see that there is a large error, 0.6 maximum error. But when you use NTK-based weights, so the error is of almost 1 order of magnitude lower than the vanilla PINN. Okay. You can also see the eigenvalues, how they are performing. So lambda R is initialized as 1 initially, and then it stays as 1. The lambda UT and lambda U, we have initialized at around 100. But then it suddenly increases. Okay, you can see how fast they are increasing. So again, we cannot use this trick, just like activation function, adaptive activation function. So the optimal value is more than 10,000 for lambda U, and for lambda UT, it is almost say 50, something like that. Okay. Okay, so again, these are 2 different ways to balance the gradients of the loss function, different terms in the loss function. There is one more easy way to do that. I think this is the most easiest way and more not efficient, but effective. This has been proposed by McLean and Braganeto recently in JCP paper. It is called SA PIN, self-adaptive pins. Okay, so they basically use soft self-attention mechanism. So which these computer science guys, they use regularly. So it's very easy. We'll directly go to the method. Now we have again 3 terms, the PD term with lambda R as the it's a vector quantity now. The difference is the previous 2 approaches, that was a scalar quantity. Okay, but now this is a vector quantity. That means it has defined for each residual points, rather than a single value for every point. Okay. Similarly, lambda B is a vector quantity which is defined for each boundary points, and lambda I is a vector quantity defined for each initial point, initial data points. So you can see these values of these vectors, and these all of them are trainable non-negative weights. So the aim is to learn these weights. So how to learn? It's basically a min-max problem. It's a two-player sum game. So what you are doing, you are minimizing theta. So theta consists of all weights and biases. So our approach is to minimize theta. But then second thing, the approach to learn lambdas we know that it should be more than 1 or stays equal to 1. Okay. So what we are doing, we are maximizing lambdas here and minimizing the theta. So it's a min-max game. Okay. So this way we are doing. So for theta, we use gradient descent method, and for this lambda, we use gradient ascent method. So we have minus here and plus here. But the issue is then if we are running for very large number of iteration, it will keep on increasing the lambda weights. Now the catch is we are not using it directly, but we are using with the masking function m of lambda. So that will actually take care of it will saturate after some time. Okay. Again, it's a parameter because you need to define the upper limit of that masking function. So there are different masking functions. They have used polynomial mask or sigmoidal mask. So if you see sigmoidal mask, you have to define what's the upper bound. Okay. So that's again a hyperparameter. But this is much more efficient because you can actually give attention to the local features. So if you have shocks or complex value in the local zone, so you don't have to increase the value of lambda everywhere, right? So I'll show you the plot, how these weights looks like after training. So let's take with the one-dimensional Kahn-Hilliard equation. So this is the equation, xt domain. So x is from -1 to 1, t is from 0 to 1. And these are the initial conditions and the boundary conditions which we have. Okay. So we are comparing the vanilla pin with the self-adaptive pin. So these are the hyperparameters. So we just use 10,000 iteration of Adam and then switch to LBFGS till convergence. Learning rate is this much. Hidden layer are 5 with 100 neurons in each layer. Okay. Okay. So this is the result with the vanilla pin. So you can see this is the XT plot basically. And this is the comparison with the exact solution. So it actually fails to capture this region. Okay. But when you use self-adaptive, it exactly captures this solution. And how the self-adaptive weight looks like, you can see that. So you have more weights here, close to 40, almost 35. Okay, and you have almost unity weights here. Okay, so these weights are increasing as per the where the loss term is large. Okay, so you are enforcing that point by increasing the weight for particular point. Okay, so these are much more effective than previous two approaches, dynamic weights and the NTK-based weights. Okay, and as far as the cost is concerned, surprisingly, self-adaptive weight had just 10% cost compared to NTK and dynamic weight, which is more costly. Because every time you need to find out the gradient of loss function in order to do the learning rate annealing thing, right? So that is more costlier than this much. Because here you're just using gradient update formula to update the parameters, the lambda values. Yeah. Yes. No, I'm showing these weights. Okay, so wherever you see large weight, that means at that point loss was high. Yes, yes. Oh, okay. It's my mistake. Yes, it should be high. Yes. Okay, so you can see that you are getting large values of this lambda at the beginning. Okay, because as you go away from the initial condition, unless your solution is correct here, you cannot get solution away from, right? So you need to make sure your solution is correct near your initial condition. Okay. So I'm not sure, should I, it's almost already, I have passes 4 p.m. So I'll just take 5 minutes and I'll quickly go through this time domain decomposition. We recently proposed the unified scalable framework for causal sweeping strategies for time domain decomposition. So, okay, this is the example I want to show you. So if you see a figure, so the bottom plot is the exact solution and the top plot is the predicted solution by PINNs. Okay. Okay, if you see, this is a periodic boundary condition. So it's just a linear convection equation, nothing else. And you have sinusoidal profile with high beta, the wave number. But it fails to capture this solution. Why? If you see, it is still satisfying the periodic boundary condition, right? Because whatever the solution you have here, it is the same solution is there at there. So this is one of the problem of PINN. So even though it satisfies periodic boundary condition, it fails to capture the solution. Okay. Second one is no propagation. If you see B, the solution is not at all propagating. It stopped here. And the C we have already seen. That's the Kahn-Hilliard equation. So it is propagating, but it's wrong. Okay. So these are some of the failure features of PINN. So what's the strategy? You start with small domains, and then first you train one domain and then attach another domain and then go on subsequently. So there are various strategies like adaptive time sampling. You start with one domain, then attach second, and then so on. Okay. Second one is backward compatibility. That means you train these red points first, find the solution, and once you get the solution, that solution will be the initial condition for these black points. Okay. So this way you are, when you're decomposing the domain, you are reducing the complexity of the solution, right? So it's easy for neural network to fit the solution. If you have large domain, then it's really difficult to fit the solution. So that's the idea. And we have already seen the XPIN. And this is again the time marching, which is similar to the adaptive time sampling. Okay. In XPIN, what we are doing, we are simultaneously training all the subdomains together. Okay. Okay. I'll skip this one. Okay. So what we proposed a stack decomposition. So for example, if you see figure, so green zone is where the training is finished. The yellow one is where you are currently training, and these are the future training subdomains. Okay. That's the time marching approach. You go one by one. Okay. XPIN, what you are doing, you are training simultaneously. All is yellow. But what we are proposing is stack decomposition. We can use more than one subdomains to train, okay, instead of just single subdomain. So that will actually increase the speed of the training. Okay. And we also use this sweeping technique, window sweeping technique, for time sweeping collocation point. Okay, so we are actually taking only those collocation points which are under training currently. We are not taking the future collocation point. Okay, and then you can use different functions, like here we use uniform, linear, or error function. This one is the error function, how to select the next set of collocation points. Okay, so this actually reduces computational burden further. We also use, along with time stack decomposition and window sweeping, we also use transfer learning strategies. That means you train the network in one domain and use same network in another domain. The only difference is your PD is same, your data points are different. So it will be easy for the network to just learn the new data points rather than learning PD again. That is called transfer learning. And fine tuning means you just add additional layers in the network along with the learned network, so that you can learn the additional features of the solution. Okay. This is the algorithm how to choose the n, so number of columns of the subdomains of the temporal decomposition, and yeah, interface. You can also choose the interface condition. We discussed a lot of interface conditions. And the window sweeping algorithm with what kind of linear, uniform, or error function to choose the collocation points. Let's see an example quickly. It's a KDV equation. So there is no way you can solve this using vanilla PINN. It will definitely fail. So with PINN, you can see the relative L2 error. But when you use stack decomposition or window sweeping, then you can actually see the error is decreasing. So this is more prominent for, this is from time from 0 to 1. But when you go for long time integration, the PINN suffers a heavy error. But stack decomposition with window sweeping, you still get good error, 1 order of magnitude, more than 1 order of magnitude. If you see comparison of training time, you need 15,000 seconds, but with stack decomposition you need 7,000. Why? Because we have already trained the network on small domain. It converges fast, and you use the same network in the next subsequent subdomain. So in terms of computational cost, it is very efficient, plus accuracy is more. Okay, so these are the we worked on theory of PINNs, where these are some of the papers. So this is the first paper which actually addressed the the first comprehensive theoretical analysis of PINN and XPIN for the nonlinear PD, Navier-Stokes equation, basically. And that's it. If you have any questions. Question. Yeah.
So are you familiar with the neural Fourier operator?
Yes. Yes. Okay. A neural Fourier operator it's not PINN. It's basically mostly a data-driven technique. So you have input data, pair of input and output data, and you are learning the mapping between the data, right? So once you train, then you can actually test it on the unseen data. So you can use, now recently they have published a physics-informed Fourier neural operator. So they also use, along with this data set, they also use physics-informed part. But it's again a PINN. If it is physics-informed, then it's PINN with different architecture. So it's just like DeepONet, right? It's a physics-informed DeepONet. It's not different from PINN, because your architecture is different. You have branch net and the trunk net, right? So that's the only difference. I can use CNN or spiking neural network, or graph neural network instead of feed-forward neural network with physics-informed part. So it's still a PINN, but then I can say physics-informed graph neural network or something like that. There are so many papers. Yeah. So, any other questions?
Hello.
Okay. Maybe I'll stop here. I don't have here, but I have in the paper.
Hello. Can you
Yes.
hear me? Which is a bit tangential, like so we all have seen the hype around language models and how single model can incorporate multiple tasks. So is there a way we can have a single model which can incorporate multiple different types of PDs for multiple different problems, and
So it
we
is
can have
it
a
is
different
also
task?
called
So
as
how would
one-shot
that
learning.
modeling go?
Basically, you can either choose the different PDs, or you can either choose different boundary condition. So there is something called as L Hydra, or multi-level PINN. Okay, so where they have actually shown that you can use different PDs at the same time to learn the solution of these PDs. Yes, you can do that.
Okay, yeah, thank you.
Yeah, so this is the convection problem, and these are the domains, subdomains which we divide. And basically, you can see this is the single domain, the blue curve. Okay, but what we are doing, we are finding the L2 error in 16 domain for a single domain, just to compare how it. So when I actually do 4 subdomain, 10 subdomain, 16 subdomain, okay, 2, 8, 14, you can see the relative L2 error is actually going down. Okay, but after some time it saturates. So there is no point on increasing number of domains. Okay.
We cannot see the screen actually.
Yeah. Okay. Yeah. Can you see now?
Yes.
Okay. So here I'm talking about the relative L2 error with single domain 2, 4, 8, 10, 14, and 16 subdomain. And these are the relative error I'm actually showing for 16 subdivisions. And I'm plotting at the center of that subdomain. Okay. So with one single domain, the error is large, but as you increases the number of subdomains, the error decreases. Okay. But then after that, it saturates. So there is no point on further decomposing the subdomains. Okay. So that's how you can learn how many subdomains you need for a particular time interval. So you can see that the long time integration issue. So you can see that for vanilla PIN, error is large here. Okay, at t equal to 5. It is a typical case because when you do long time integration, your error is very large at the large time step. But when you use time domain decomposition, the one which we use, then you can see the error is decreasing substantially. When you have space, you have boundary condition. When you have time, you don't have anything on the right-hand side, right? Is the final solution you have. So that's why I specifically say long time integration. Any other question? If not, let's stop here. And if you have any question, you can email me later. I would be happy to answer those questions.